Welcome to lecture 8. This is going to be a short lecture on revisiting what we did in the last lecture on polarization. So in the last lecture, we showed that Maxwell's equations admit plane wave solutions. Maxwell's equations admit plane wave solutions and these were of the form E was E naught e to the power I k dot x minus omega t, and B was B naught e to the power I k dot x minus omega t. E naught and B naught are called here, E naught and B naught will be called the polarization vectors of the electric and magnetic fields. These are complex three-dimensional vectors. The wave vector k and the angular frequency are real, and in vacuum they are related by omega squared is equal to c squared k squared, or omega is equal to ck. So omega is equal to c mod k, if you wish. So which is equivalent to, last time we were also writing this as omega squared is c squared k squared, and this is the same thing. Okay, so in addition, what we found is that we also found that B naught was 1 over omega times k cross E naught, and we found that k dot E naught is equal to 0 equals to k dot B naught. So now, what this particular thing means in a sense is that the modulus of E naught is equal to c times the modulus of B naught. So this meant that the polarization vector of the electric field, the polarization of the magnetic field, and the direction that the plane wave is propagating are all orthogonal. Okay. To see how much freedom there is left in the plane wave, it's helpful to choose coordinates. And for example, we looked at the plane wave traveling along the x-axis. Let's for convenience sake just do something else in this lecture. So let's say we'll define z to be the direction in which k vector points. So so let's look at E vector being equal to E is equal to E vector and e to the power I omega. We're going to put z over c minus t. So for plane wave traveling along the z-axis. In this case, E naught is orthogonal to k, so we will write E naught as Ex, Ey, and 0, with Ex and Ey being complex numbers. Very good. Now, the two complex amplitudes, Ex and Ey, each have magnitudes and phases. So we will write these explicitly. So Ex is magnitude of Ex, e to the I phi x, and Ey is magnitude of Ey, I phi y. Okay. So one needs 4 real numbers to specify this polarization vector. So 4 real numbers are required to specify the E naught, which is the polarization vector. Okay. Usually we will separate the phases into an overall phase and the difference of phase between Ey and Ez. The reason for doing that is as T and Z change, the phases of Ex and Ey change in the same way, while this difference of phases will remain unaffected. So we will call phi as phi of x minus phi of y. So this is the difference of phases between Ex and Ey. So phase difference between Ex, Ey. And we will take, so what we will do, we will usually not care about the overall phase or the overall magnitude, but thus to specify the vector, we speak of the relative sizes of Ex and Ey and the phase difference phi, which is phi x minus phi y. So now don't let these complex polarization vectors confuse you, if you wish. So we can of course as well write E as Ex into x cap cosine of kz minus omega t plus phi x, and Ey y vector cosine of kz minus omega t plus phi y, where you see explicitly the four real numbers which specify this polarization, right? Just exponentials just make this algebra a lot easier. All right. So next, just let's move into linear polarization. So linear polarization okay, so now so we say that a plane wave is linearly polarized when there is no phase difference. So linear polarization is when there is no phase difference between Ex and Ey. So what we will do, so So and we will choose the overall phase. So we can, so let's write this. So E naught is Ex, Ey 0, and we will choose the overall phase such that Ex and Ey are real numbers. Choose overall phase such that Ex, Ey are real numbers. Suppose Ey is equal to 0 and Ex is not equal to 0. And if Ey equal to, this is exactly what we had done in the last, well, very similar to what we had done last time around. Then we have, so we have E as E naught x cap into e to the I kz minus omega t, where E naught is equal to modulus of E naught vector. This is just a number. Okay? And again, you know, like we saw last time around, what we will see is that B is 1 over C E naught, now y cap e to the I k dot k z minus omega t. This configuration is said to be linearly polarized in the x direction. Okay, so this is configuration is linearly polarized in the x direction. Very good. So you can, of course, now, you know, have something which is also linearly polarized in the y direction. In that case, you know, E is going to be given as E naught y. So similarly, E as E naught y e to the I kx minus, sorry, kz minus omega t, and B as minus 1 over C E naught x e to the I k z minus omega t is linearly polarized in the y direction. Okay? Let's just say a few more things, that we implicitly want to have the real parts of these fields. So for example, for linearly polarized light in the x direction, so this is going to be the real part of E, which is E naught cos of kz minus omega t 0 0, and the real part of the magnetic field, which becomes 0 E naught over c cos of kz minus omega t 0. So there, as you can see, there is no x or y dependence in these fields. The fields are completely uniform in x and y. So these are plane waves. So at each point on the plane wave, the electric field points in the x direction with the same magnitude. This magnitude varies as we move in z and in t, but is always uniform in the plane. Okay. So if you look back at the picture that we have drawn here, so what is going to happen is that, so this in a sense is the direction so this is B, this is B, sorry. So this is what it is. So if we are looking at linearly polarized light, I mean along the x direction, so this is what is going to happen. So this is B, this is E, and that is the k vector. And so this is how this field actually, this is how the fields will change as we move along a wave in the x direction. Here it's in the k direction, but so let's just note here that no dependence, no x or y dependence. In these solutions. Fields are completely uniform. In x and y, these are plane waves. Each point on the plane, the electric field points in the x direction, and it has the same magnitude. Each point on the plane, electric field points in x cap direction and has same magnitude. This magnitude varies as we move in x, z and t, but is always uniform in the plane. So this magnitude varies in z and t, but is always uniform in the xy plane. Okay, so this is what you have for a plane polarized light. Now we'll move on to circular polarization. Okay. So what happens when the components of the electric field are not in phase? First, suppose they have the same magnitude but are a quarter wavelength out of phase. So what is happening is, 5x minus 5y is equal to pi over 2. Okay. Suppose that's the case, then E naught is what? It's E naught, and E naught e to the I pi over 2 and 0. So this essentially means that this is E naught and I E naught and 0. So this electric vector is thus E naught e to the I k z minus omega t, I E naught e to the I k z minus omega t, and 0. So if you write the real part of this down now, this is E naught cos kz minus omega t minus E naught sine kz minus omega t and 0, right? So this is called left-handed circularly polarized light. What does this look like? Let's do this. Let's look at the picture that you have, that I have for you here. So at t equal to 0 and z equal to 0, the electric field is, so at t equal to 0, z equal to 0, real part of E is given by E naught 0, 0, okay, pointing in the x direction, okay. If you move along a little further, when kz is equal to pi over 2, still at t equal to 0, then so at t equal to 0, z equal to, sorry, not z, kz equal to pi over 2, then the real part of E becomes 0 minus E naught 0, which points in the negative y direction, okay. So further along, if kz equal to pi, it points along minus x and then y and so on. After a full wavelength, it gets back to x again. So what is happening is that as we move along z, the polarization rotates clockwise in the yz plane. Okay. So further along, so let's write this down. When kz is equal to pi, when kz equals to pi, it points along in the x minus direction, and then at it points along minus x cap direction, and then at y cap and so on. So after a full wavelength, it goes back to x cap. Okay. So thus, as we move along y, as we move along the direction of propagation of the wave, so as we move along z, the polarization vector rotates clockwise in the xy plane. Equivalently, at a given z, as time progresses, it also rotates in the xy plane. So the picture above should actually make this clear, and yes, that's what we have. So now simply you can start off by looking at phi x minus phi y, and you can make this equal to minus pi over 2, and then the electric field E naught is going to become E naught minus I E naught 0. So that means that the real part of E will now become E naught cos kz minus omega t, E naught sine kz minus omega t, and 0. This is right-handed circularly polarized light. Circularly polarized light. Notice if we add a right-handed and a left-handed polarizations, then E naught, if we add left and right-handed, polarizations, what do? We start off with E naught. So this is E naught I E naught 0 plus E naught minus I E naught 0, which is twice E naught 0 0. So this is actually, so this we get a linearly polarized light in the x direction. Similarly, subtracting them will give you a linearly polarized light in the y direction. So now you can see that circular and linear polarizations are not independent. Indeed, any possible polarization can be written as the linear combination of left-handed and right-handed circularly polarized light. Circularly polarized light has okay. So let me write this down for you. Circularly polarized light and linear polarization. Circular and linear polarizations are not linearly independent, and another important thing is any polarization can be written as a linear combination of left-handed and right-handed circularly polarized light. Okay. Circularly polarized light has some angular momentum with the positive sign, with one sign for the left-handed and one sign for the right-handed light. Linearly polarized light carries no angular momentum. It's that's easy to understand because it's the sum of the left and right-handed lights. So so as an analogy, you can think about two tops, maybe one spinning clockwise and the other spinning counterclockwise. So the two-top system will have no net angular momentum. So as we light cannot have arbitrarily small intensity. The smallest intensity of light can be a single photon. So this must mean that the photon itself is polarized, and single circularly polarized photon has some amount of angular momentum. It may seem surprising that photons, which are point-like particles with no substructure, can have angular momentum of their own. This is very odd actually, but it's true nonetheless. Photons actually have spin, and we say that photons are spin-one objects. The two signs of angular momentum correspond to the two helicities of the photon. So finally, to complete the discussion on polarization, we can also look at varying magnitudes of different components of the phase. So the most general parameterization is the following, which is E naught is Ex x cap cos of kz minus omega t plus Ey y cap cos of kz minus omega t plus phi, where when Ex and Ey are different and the relative phase is non-zero, polarization changes in magnitude as it rotates in the xy plane. It therefore describes an ellipse, and this is called elliptical polarization. So let me just write this down. When Ex, Ey are different, and the relative phase phi is non-zero, polarization changes in magnitude. As it rotates in the xy plane. Thus describes an ellipse and this is called elliptical polarization. Linear polarization would correspond to phi equal to 0, and circular polarization corresponds to phi equal to plus minus pi over 2 and Ex equal to Ey. So that's what I wanted to. So this in this short lecture, this is what I wanted to do, because I thought that the previous discussion on polarization that we had was a little hurried, and I was not able to give you much details here. But I hope this is clear now. And we will go on next time around with another full-fledged lecture discussing other aspects of electromagnetic waves. In particular, next time around, what we're going to do is we are going to look at, the energy that is carried by the electromagnetic waves. So we will start off by revisiting what we did for what you have hopefully earlier seen for the electrostatic and magnetostatic case. We'll go through that quickly, and then look at how energy is carried by these waves, electromagnetic waves. All right, see you guys then.